Hi, class. Today we're going to start our first of 5 lectures regarding the history of the atom, or really more accurately put, our history of our understanding of the atom. Okay. So let's start off. First thing we got to do, though, if we're thinking about an atom, we got to talk about a model. And no, I'm not talking like a model that you would see in a magazine or on TV. I'm talking about a model. This is something to help us understand or explain something. Right? So it's think of it kind of like a picture, or I can think of here I've got a little matchbox or a little model of a car, right? And if we're trying to attempt to explain something like this, so if we were going to go over to, so if we met some aliens and they'd never seen a car before, what would we do? You'd take this and you just kind of show them, well, here's what a car looks like. And you'd be able to describe it and say, well, usually it has 4 wheels on it, and it's got a front and a back, and it's got doors that we can get into. And they're like, oh, okay, that makes a little bit of sense. But this is a very simple model, right? This doesn't function, perform, act. It doesn't have the same size. It's not exactly what a car is. It's just a model. It's an attempt to explain it. Now, so this is a real simple one, but we could get a little bit more complicated, right? So here I've got another example of a model. So again, here's our model. It's got 4 wheels. It's got some doors, but this model gets a little bit more functional. Right? So the top comes off on this, just like on a Jeep, the top will come off, and the windshield can fold down, again, just like a Jeep where the windshield can fold down. And this one even has a hood that can open up, and you can look inside and you can see a bit of an engine. So this one's a little bit more complicated than the first one. Oh yeah, and I think this one can even, this one can steer. So you can see that the wheels can steer. Our first little model car couldn't do any of those. Now they're still very similar, right? But as we can make our models a little bit more complicated and keep getting closer and closer to reality. And that's really what I want to talk about here in our next point, right? We can get them closer and closer to reality. Now, one thing before I keep going down that track is the idea that what do we use models for? Besides explaining what things might be to somebody who's never seen them, usually when we're making a model, it's because something is either too big or too small to demonstrate. Right? So if somebody wanted to know what a pen looked like or what scissors looked like, for example, I mean, we could just take a pair of scissors and hey, here's what scissors look like. Right? It's not hard. It's a size that's easy for us to carry around, show people. But we can't really carry around a car real easy. It doesn't work. Or let's talk about things that are really more in the realm of science. And we're going to be talking about atoms here. Right? Atoms are super, super, super small. You can't see them. So it's not something you can actually take a look at. And similarly, we can make models of the solar system or the universe, right? Way, way, way too big to be able to just say, hey, look at this. We take those models and we usually do them when things are too big or too small, and we try to get it into more of a human size so we can get a better feel for what it is and some of its properties. Now, I started just a minute ago talking about how we can make a simple model like this little matchbox car, right? This one doesn't have wheels that turn, has no doors, nothing like that. And we can get a bit more complicated, and I showed the model then in my Jeep where the top comes off and the windshield goes down and the hood comes up and it shows a little bit of the engine and the wheels turn. But we can still get even more sophisticated than that, right? Because we know cars move. Right? So here's another little version of a car. And for this little car, right, this guy, I can turn him on, and he's got a flashing light. His wheels will turn. So this car can move, right? It can move. So we've made our model a little bit more complicated. And then I can take another model of a car. So notice they're getting a little bit bigger as I do this. So here I've got a radio-controlled car, right? So I can turn on my radio-controlled car, and right now it moves, right? Its wheels will turn, it will move, right? I can get it. Now this one can go forwards and it can go backwards. Or the little blue buggy I just showed you, it can only go forwards. Now this one, I think I fried the motor on it, but this one, it can actually turn its wheels on its own, right? I just think I've killed my motor or my batteries are a little weak. But again, what are we seeing here? We've got a model of a car, and we can keep making it a little bit more complicated. Right? So the more we learn, the more we can do with things, right? So they're always going to fall short of reality, because if it's really a car, then it's a car. It wouldn't simply be a model of a car. And not only are they going to fall short of reality, as time goes on, our models get more complicated, right? We start off with a simple little matchbox car. We then went to a car that had pieces that moved. We went then to a car that could move on its own. And then finally, we went even to a car that not only could it sort of move at its own, it could turn. We could control it from a distance. It could go forwards and backwards. We don't just push it like the first, like my little red Jeep, or turn it on like the little blue buggy. It's gotten more complex. Still has a way to go. It's not a real car, but it's getting pretty doggone close. We get a good feel for what the car does as our models get more complex. And the same sort of thing has happened when we talk about atoms. Now, this is the big idea. Why do the models get more complex? Why do they get more complex? Because we've learned more. Right? If you're trying to explain a car, hey, here's a car. Yeah, it has four wheels, it rolls. But we know the cars have engines. So we got to have a car that has an engine. Well, so we can make a picture of an engine like we have here. Well, that still doesn't really do all the trick. We can actually put a little engine in it. This one has an electric engine so that it moves. Right? We can keep going farther. You could even go to the point where we have little cars that are gasoline powered. So they're very similar to a car. We keep getting more and more complex because we've learned more and more about the system. Right? None of those cars I just showed you have brakes. Well, we know real cars have brakes. There's another part of the complexity that we would want to put into it. They have transmissions, so we can shift gears. They have windows that go up and down. We can keep going on and on and on. We can make them very, very complex. At some point, though, it's a model. It's never going to be like the real thing unless you have the real thing. More complex because we get more information. And that's what we're doing with our atom. When we first started out, we had no idea what an atom was. We didn't know what we were talking about. And it took us a long time to get to our current understanding of the atom, which is actually quite complex. The first person that we credit with coming up with the idea of atoms was a man by the name of Democritus. You just see here from my slide, he lived a long time ago, right? 2,500 years or so ago. And he was the one that we credit for coming up with the idea that atoms existed. At this point in time, most people thought there were only four elements, right? Air, wind, earth, and fire. Yeah, air, wind, earth, and fire. That everything was made of one of these four elements. Well, Democritus didn't quite think it was that simple, and he kind of made the observation that, well, we could take something, right? We could take a little stick, we could break it in half, we could break it in half and break it in half. We could keep making it into smaller pieces. But he's the first one that came up with the idea that at some point you can't break it apart anymore. You've got a fundamental, smallest little building block. And he called those atomos. That's the Greek word for indivisible, smallest piece. Okay. Very intelligent. The thing is, though, he had no proof that these atoms existed. Why? Well, because atoms are really, really, really small. And we didn't have much technology back then. But he was smart enough to at least realize that this something had to be the smallest little building block, and everything was built out of those. Well, about the same time, actually just a little bit later, they did overlap a bit, was a man by Aristotle. And you've probably heard of Aristotle before. He's much more famous. And Aristotle, he did not believe in atoms. He strictly believed that things were made of earth, air, wind, or fire. Now, because Aristotle was very smart, he was very good at explaining lots and lots of different things. People said, well, if Aristotle says it, it must be right? Kind of like with us, if you're going to go to want to learn how to play basketball, and I'll tell you, I don't know much about basketball, but if you're going to go into the gym and you want to learn how to play basketball, are you going to listen to me? Or if Michael Jordan walked into the room, or LeBron James walked into the gym, would you listen to them? Well, heck yeah, they know we know they know how to play basketball. We know they know what they're talking about. So you're going to trust them in basketball over anything I would say, because you have reason to, right? They've got a good track record. Same thing was happening with Aristotle. He was right about so many things. And they said, well, if Aristotle says atoms don't exist, they must not exist. Now, I'm not saying it's necessarily a good thing or a bad thing. That's just kind of the way humans are. But the impact of that was that it was another 2,000 years before anybody started thinking about the idea of an atom again. Aristotle had that strong of an influence, 2,000 years before somebody started to say, well, wait a minute, maybe Aristotle wasn't quite right. Maybe there is something to Democritus' idea that we have something called atoms. So, wow, big impact simply because a very important person. And I'm not saying that he was dumb. He just had an inaccurate understanding. He didn't have enough knowledge available to him. And I'm sure if he did, he would have been able to explain atoms and take it a little bit further. But let's fast forward 2,000 years, and now we're starting to get some evidence, right? Unlike Democritus, now we're getting some evidence that atoms actually exist. And the first one we want to talk about here, this was a man by the name of Antoine Lavoisier. Now, what Lavoisier was doing, he liked to do experiments where he'd do them in a closed container. So he knew what something was coming and going. He knew everything was stuck inside of that container. And he started to realize that that no matter what he did, what kind of chemical reaction he did inside this container, the mass didn't change. The mass didn't change. The mass of the container before the reaction was the same as the mass of the container after the reaction, even though by looking inside the container, it looked like it contained different things, right? We could have, like I mentioned, I did earlier with the candle burning, right? We can see the candle, it's a solid, it gets smaller and smaller and smaller. And we saw that it weighed less when we did that in the classroom. Well, why? Because when the candle burned, it turned into gas, and that gas floated away. We weren't keeping the gas in our container. Stuff that Lavoisier was doing, he was keeping things in a container. So he came up with the idea that really, if our mass is conserved before and after, what are we really doing? Well, he thought that maybe we just have these little pieces, and I'm kind of trying to show that here in the slide here. We have this piece called an S, and we have this piece called an O, and another piece called an H. Right? And if we mix this substance, it's made of one S and two O's. When we mix it with another substance, it's got two H's and one O, and the total mass of these guys is 5 grams. Well, he knew that these would react, and they're going to make something different. And there's something different. Let's just say he didn't understand all this, but he knew it made something different. All we did is we rearranged them. So on the right-hand side of our arrow in our product, right, we still have 2 hydrogens. Well, that's what we had on the left. We still have 1 sulfur because that's what we had on the left. We still have 3 oxygens on the right because that's what we had on the left. So all we did is we moved our puzzle pieces around. We recombined them. He was smart enough to realize that, and that started leading him to go back, well, maybe there is some concept of their idea of there's this small building block that things are made out of. Now, he didn't make that connection yet, but by making his observation that the mass didn't change and that we probably have things that are moving around, he was starting us back to that idea that atoms are small and indivisible. So the next thing that came around was a man by the name of Joseph Proust. Now, we're going to see that most of these people are men, just because that's the way society was, and I guess to a large part still is mostly dominated by men. But we do see some women that are famous for it. You can look right outside my classroom in the hallway. There are some posters of some very, very famous female scientists, and hopefully we'll see a lot more of those. The more diversity we have, the more thought we have, difference of thought, the better we're going to get at understanding things. All right, so Proust came along, and he further was going on with he noticed, well, here what he did kind of at the bottom. He took water, and he was doing electrolysis of water. What does that mean? He ran electric current through it. And he realized that whenever he ran this electric current through the water, what was happening? He would produce 2 hydrogens, or 2 of these things that he was calling hydrogen, and for every 1 thing that was called oxygen. And he was kind of doing that because people were saying, well, the water in France is different than water in England, it's different than water in Spain, different than water in Europe. And he was kind of saying, well, no, if you look at it, water is always the same. It's always going to break down into 2 parts of this hydrogen thing and 1 part of this oxygen thing. No matter what it is, that's what water's made out of. So he was the one who first started coming back and say, wait a minute, if we're going to have these compounds, and water is an example of a compound, there's a definite proportion between the parts that make it up. Right? Water, 2 hydrogens for every oxygen. Normal car, 4 wheels for every car. 2 doors, or maybe 4, depending on the car. Right? 1 driver, 1 steering wheel. Right? There's these definite proportions that he was seeing. Right? So he went on, and he came up with an idea. Again, he was doing it through electrolysis, and he made the observation that H2O2 It's still made of hydrogen, it's still made of oxygen, but the proportion is different. And if the proportion is different, it's a completely different compound. And you might have heard of H2O2. We call it hydrogen peroxide. And we will actually use it sometimes if you get hurt. Right? We'll pour a little bit of hydrogen peroxide on the wound, and you'll see it bubble as it is breaking down. And it's very good at being an antibiotic, but a very different substance than water. We don't want to ingest H2O2. It could cause us a problem. There's a nice old chemistry joke that the chemist walks into the bar and says, "Bartender, give me some H2O." And so the bartender pours him a glass of water and goes ahead and drinks it, and it's fine. Then the next person walks into the bar and says, "Hey, that looks good. Bartender, give me some H2O2. Now, he's trying to say H2 also, but he said H2O2, and the bartender heard 2 hydrogens, 2 oxygens, and he gave him some hydrogen peroxide. The customer promptly drank it, and promptly died. It's a very different compound, right? Same stuff, same atoms, put together in a different way, different proportions, very different impacts. And Proust was the first one to start thinking of this, start realizing that compounds have a definite proportion, a fixed proportion, just like we talked about a little bit earlier in the year when we were talking about the difference between an element and a compound. Well, we go a little bit farther forwards, and then we run into a man named Dalton. Now, Dalton was a very interesting person as it goes through. Dalton was very smart, but at the age of 11, he had to stop his education to get a job so he could work to get food and help with his family. But not long after, a year after, the school teacher in the area died, and they needed somebody to be a school teacher. And these people realized that Dalton was pretty smart. So at the age of 12, Dalton became the teacher of his little community. Well, this was really good because Dalton, not only was he smart, now that he's 12, he's young, he's getting used to explaining things to people in a way they can understand, right? So we have some very smart people, and they can't always explain what it is that they're talking about, or explain it in a way that's easy for a normal person or an average person to figure out. Dalton had that gift. He could explain things in a simple way that you didn't have to have years of education to understand what he was talking about. So what he did is he came together and he put these different pieces together that we already had. We came up with a theory. And his theory was that all matter is composed of atoms. All right, it's composed of atoms. And these were the indivisible, these indestructible little things that Democritus had proposed 2,500 years ago. All right. He further then went on and said, not only are they composed of atoms, but we have this idea of elements. In our point 2 here, all atoms of the same element are identical. Every oxygen atom is just like every other oxygen atom. Every hydrogen atom is just like every other hydrogen atom. Kind of makes sense. But until you have that rule kind of made very clear, it's not always obvious, as it seems. It's obvious to us because we've heard this since day one. And closely related to point 2 there was point 3, that atoms that are different elements, they're different. Well, that's kind of what makes them a different element. They're a different atom. And then finally, he incorporated the idea, his 4th point here, that compounds are composed of 2 or more different atoms or different elements. And not only are there 2 or more different elements, but there's a definite ratio of them. So why did this work? Why did Dalton's theory come together so well and it helped people understand? Well, number 1, it was pretty simple. But number 2, if you look down here at the bottom of my screen, he used things that people were already familiar with. The law of conservation of mass that Lavoisier had proposed a couple decades before. Right? People were familiar with it. They understood that. And the law of definite proportions that Proust had also put together here a couple decades earlier. What was different with Dalton is he put things together. It wasn't just a one-off thing. He started putting things together. So I'm just saying, yeah, a car's got 4 wheels, and then somebody else coming by and saying, yeah, a car has 2 doors. But they're saying different things. A car has 2 doors, a car has 4 wheels. Dalton's coming and saying, no, yeah, a car has 2 doors, and it has 4 wheels, and it has 1 steering wheel, and I don't know, we can say it's got a hood, a trunk, whatever. We can put a couple different things in. But Dalton was packaging it together, putting it all together. And he did this in a way that was easy for people to understand. That's part of why his idea then took off so quickly. All right. That's where we're going to stop for today. Tomorrow, we're going to continue on with our second part of their notes of the atom. Don't forget to take your 3-point lecture notes quiz today, and we'll talk again tomorrow as we go into lecture 2. Thanks, class. Bye.